So we're now going to be introducing some different notation to solve derivatives, derive functions, and also look at higher derivatives. So not just deriving an equation once, but finding, the second and third derivatives. So the continuous derivatives of the same function. So basically, the notation we're going to use over here today is this dy over dx notation, which basically, it's not necessarily a fraction, but it's just a different way. So all of notating the same thing. So far we've been saying that if you have a function f of x, for example, let's just go for a simple f of x is equal to x squared, we could say f dash of x to note the derivative, right? This dash really stands as a derivative. Now what we're saying is instead, if the function is defined as y is equal to something, so let's say if y is equal to x squared, then what we say is we use dy over dx as a way of saying we are deriving the equation y with respect to x. Okay, because the x is the is this part, this is the input that we're deriving, right? So that's just what it means. Okay, and then if you're doing second derivatives, then we're saying we're deriving this again. So we're deriving dy again with respect to x again. So that just becomes true, and then so on and so forth. Okay, that's basically the idea behind this notation. So it means the same thing. It's a different way, depending on whether you're given a function defined as fx or if you're given a function defined as y. Okay. So if you go to the first one, we want to find the first, second, and third derivatives of each of these three functions. The first one, y is equal to x to the power 7 plus 4x. And now finding the first derivative, again, we're going to use that notation. We have dy over dx. Again, we're going to use our same rules. So x to the power 7. So we've got 7 comes down, where 7x, and then the power decreases by 1. Okay, 7x to the power 6, and this just becomes 4. Okay, so that's our first derivative. Now finding the second derivative, we do d squared y over dx squared, and again, following the same rules. The 6 comes down, so we do 7 times 6, which is 42, and the power reduces by 1. Just fine. And since this is just a constant, we can just get rid of that. So that's just the second derivative. Okay, and then the third derivative, so now we have d cubed y over dx cubed. It's not really a power, it's just a way of saying it's first, second, or third. And again, we're doing the same thing. The 5 comes down, so we do 42 times 5, which is 210, and the power reduces by 1. Okay, just to highlight those, this is our first derivative, 7x to the power 6 plus 4. Then our second derivative is 42x to the power 5. And the third derivative is 210x to the power k. And you can see with a function like this, you can keep deriving it and keep deriving it. And yeah, it has the application of finding the second derivative and third derivatives. We'll learn later on when we're doing more application-based calculus. But for now, it's just a good thing to know, and a good idea to know that we can keep deriving a function. If b, we've got another equation, y is equal to half x to the power 4 minus 7x squared plus 1. Again, finding the first derivative, dy over dx. So we bring this power down, half times 4 becomes 2, and the power reduces by 1, so you get 2x cubed here. Same thing here, 2 comes down, 7 times 2 is 14, and power gets reduced by 1. So it's just now 14x to the power 1, and then this is just a constant, so you can just get rid of that. So that's our first derivative. Second derivative, again, bring the power down, 2 times 3 becomes 6, and we go from a cube to a squared, and then 14x just becomes 14. Okay, that's our second derivative. And then the third derivative is equal to, again, same thing, power comes down, 6 times 2 becomes 12, and power gets reduced by 1, so it just becomes 12x. So again, highlighting our three derivatives, dy over dx. First derivative is 2x to the power of 3 minus 14x. Second derivative is 6x to the power of 2 minus 14. And then third derivative is 12x. But then when I'm finding second and third derivatives, we're not changing the rules or anything. It's the same process. It's just keep on deriving until you're left with nothing. So if you want to find if I was just doing this quickly, if I was to find the fourth derivative of this, if I was to derive this again, we'll get 12. And then if you derive this again, you'll just get 0. And then you've got nothing left after that. Okay, and then part C, y is equal to x squared and brackets 3 minus x cubed. So again, we've got a multiplication here to do first. We're going to expand that out. So 3x squared and x2 times x to the power 2 times x to the power 3, it becomes x to the power 5. And just to clarify, this is still y. We haven't derived yet. So now we can start deriving. So dy over dx, our first derivative. Again, 2 comes down. And 3 times 2 becomes 6. 6x to the power 1 minus 5x to the power 4. Okay, that's our first derivative. And I'm just going to get rid of this 1 here because we don't need to show that. This looks a bit weird. Then we've got d squared y, or well, dx squared for our second derivative. So 6x just becomes 6. Then we to derive this, 5 times 4 becomes 20. And our power reduces by 1. So that becomes 20x to the power of 3. And then lastly, finding our third derivative, we have 6 is a constant, so we get rid of that. And then 3 times negative 20 becomes negative 60. And then the power reduces by 1. Okay, so again, to highlight and summarize, the first derivative is 6x to the power of 6x minus 5x to the power of 4. Second derivative is 6 minus 20x to the power of 3. And third derivative is negative 60 x to the power of 2. So that's just explaining the concept of second and third derivatives. The reason why we need them, we'll learn later on. And it's basically to find the nature of turning points and inflection points and things like that. So it's mostly used when we want to sort of graph these functions and graph derivatives. These terminologies of finding second and third derivatives become really useful. Also later on, when we go to optimization problems and calculus, second and third derivatives also become very important. But yeah, we'll touch on that in the future, and we'll sort of see, you'll sort of see more about how important and why these are so useful.